So this is a little math review that will be very helpful when we derive the formal equations that govern fluid motion. Optional review for you here if you want to see the derivations and understand them. This is where it comes from. And that's the way that I understand things best. But anyhow, what we want to talk about here is some equation, right? There's some curve, some function that goes up like so. And we could call the x-axis here x and the function here some f of x. And so if we evaluated f of x at a value x, we would get some point here that looks like so. The question is, what's the value up here at, say, x plus some delta x? And what a Taylor series lets us do is approximate that. And what we're going to do is we're going to start by saying that f of x plus dx is approximately equal to f of x. In other words, we're just going to come straight over here and say, well, there's that. The problem is there's also a little bit more to that, isn't there? So as a first approximation, we could say, well, let's take the slope of this line here, aka the derivative, and add that to it multiplied by some delta x to offset it. And so we could do something that looks like the derivative of the function, say df dx. We can evaluate that at location x. And then if we multiply it by our gap here, delta x, right, this is like a df over dx, so dx times, those will cancel out. We get an offset that brings us closer. And so we could keep doing this idea, right, where first we evaluate it just by saying it's the same, then we correct that estimate by writing the slope, and of course you could do this with the second derivative to close the gap even further, right? We could do something like d squared f dx squared, evaluate that at x, and we have to multiply it by a delta x squared over 2. And you could just keep going. That's a Taylor series. What we're going to do, though, to make this useful for us, is that we are going to shrink delta x such that the following thing becomes true. We want f of x plus delta x equals f of x plus df dx at x times delta x. In other words, we're going to make it so small that we get to get rid of the approximate equals and say they're actually equal, because if this is small enough, the error associated with the second derivative in the higher order terms goes away. And what that's going to let us do is write a thing that looks like the following. F of x plus, instead of delta x, if we shrink it, we're going to have dx, right? And so that will be f of x plus df dx evaluated at location x times dx. And I'll show you in the next video, as we derive the pressure equation, how this becomes quite useful.